Jule Bachcho, I am Rigzin Amgyal, lecturer in physics. Today I am going to start a new chapter of class 12 physics. The chapter is dual nature of matter and radiation. Bachcho, as you know, if you see around yourself, you find two things around you, matter and radiation. What is matter? Anything which has mass, occupies space, is called matter. Matter may be in the form of solid, liquid and gas. For example, this is board, this is matter, and chair, the TV that you are watching is matter. So these are all matter. And the next one is radiation. You see radiation around you in the form of sunlight that we are receiving from the sun, the light coming out from the electric bulb. These are all types of radiation. So we in general we can say that we have two things in universe. The universe is composed of two things. That is radiation, and the second one is matter. If we talk about the radiation, that is light, all microwaves. Microwaves are of various ranges depending upon their frequency and wavelength that we have studied in the previous chapter, in the chapter of electromagnetic waves. So these are all types of radiation, and now we will see the nature of this radiation. What are the nature of this radiation? Then as per the classical physics, which is the physics up to the 19th century, till the end of 19th century we can say this nature of radiation is known as wave nature. Wave nature. Wave nature of radiation is confirmed and was established by many phenomena like interference of light, interference. This interference was explained by a young double slit experiment which you have studied in the previous chapter, that is in the optics. Now then diffraction, similarly polarization of light. These are some of the phenomena which are on the basis of which we are explaining it on the basis of wave nature of light. What know about the matter till the end of 19th century was that the nature of particle is nature of matter is of particle nature. Particle in nature. As we all know that all matters are made up of small particles, atoms, and these atoms are further divisible into its constituent particle. Inside the nucleus we have neutrons and protons, outside the electrons are revolving. This is what came to know up to the end of 19th century, which is also known as classical physics. Now if, once again if I go to the radiation, the nature of this radiation is considered as a wave nature, which could be explained on the basis of interference, diffraction and polarization. But earlier to this theory, Newton gave his corpuscular theory. Corpuscular theory. According to this theory, It was given in around 1675 years. According to this theory, Newton said that the nature of radiation is of particle in nature. But since there was no proof, so this theory was neglected, or this theory was, we can say, not considered as a final theory. Huygens give another theory that is wave nature of light. On the basis of wave nature of light, in 1802, Young double slit experiment. Through the Young double slit experiment, Young tried to explain the interference of light on the basis of wave nature of light, and he able to clearly explain the interference of light on the basis of wave nature of light, and then diffraction and then polarization. These are all some of the phenomena which we are explaining on the basis of wave nature of light. Now, in the end of 19th century, or we can say in the beginning of 20th century, that it came to know that it has another nature, that is particle nature. The radiation has a particle nature also, and this theory was supported. This theory, that is the particle theory, was supported by some phenomena, we can say, photoelectric effect. Photoelectric effect, Compton effect, these are some of the phenomena which were observed in the beginning of 20th century, and this could be explained only on the basis of particle nature of light, not on the wave nature of light. Wave nature of light failed to explain these phenomena, that is photoelectric effect, Compton effect, etc. This one, that is the photoelectric effect, this is in your syllabus, so this will be our topic today. That is photoelectric effect will be our today's topic. We will discuss in detail about the photoelectric effect, what is photoelectric effect, and we will see the result that we get from this photoelectric effect. And Einstein, who put forward this photoelectric effect in 1905, and he was awarded Nobel Prize in physics in 1921. So why he was given this credit for the photoelectric effect? Because he was the one among the scientists who gave the photoelectric equation, and that could clearly explain all the laws of photoelectric effect. But prior to the Einstein, this photoelectric effect was also observed by Hertz in 1887, and then it was carried forward by Helmholtz and Linus from 1806 to we can say from 1806. This photoelectric effect was first observed by Hertz. During his experiment of electromagnetic waves, so he observed this photoelectric effect in 1887. Then it was carried forward by Helmholtz and Linus. Helmholtz and Linus from 1885 to around 1886 to 1902. That is the beginning of the 20th century. After this, Einstein gave the final theory of this photoelectric effect in 1905 with his photoelectric equation. So these are some history of the photoelectric effect. Now, Similarly, we have seen that now the radiation has dual nature, so it plays double role. Sometimes it acts as a wave nature and sometimes it acts as a particle nature. And this wave nature of the light is supported by some phenomena like I have written here, and similarly the particle nature of the light is also supported by and confirmed by some of the phenomena those are photoelectric effect, Compton effect. Like this we have another effect, that is Stark effect. This Compton effect and Stark effect you will study in the higher classes. Okay, similarly around the same year, that is in around 1923, a PhD scholar D. Broglie, in his PhD thesis he submitted a hypothesis, that is according to that thesis hypothesis, he said that matter has also dual nature. That means this matter has also wave nature. This was just a theory, or we can say a hypothesis submitted by the D. Broglie in 1923 in his thesis submitted during his PhD degree. Then this wave nature, at that time there was no experiment to prove that whether the matter has a wave nature or not. But then it was in around 1900, Germer and Davison perform an experiment. Germer and Davison. They perform an experiment in which they saw that electron, which is a material particle, has showing diffraction, and the diffraction is only possible if it has a wave nature. So from this we can conclude that this matter has also a dual nature, both particle as well as wave nature. And the D. Broglie, the hypothesis of D. Broglie only give the just an hypothesis without any proof, but it was then later proved by the German and Davison that electron, which is a material particle, has also wave nature. So this is what we have studied, that radiation and matter both plays a dual nature. Now we come to the today's topic, that is photoelectric effect. So we will see what is photoelectric effect. Now before I go to explain the photoelectric effect, let me to give you another important definition, that is work function. Work function. What is work function? Students, let us suppose we have a metal conductor, and then you know that metal conductors consist of large number of free electrons inside it. It has large number of free electrons inside it. These free electrons, even at room temperature, they moves with and velocity of 10 raised to power 5 meter per second. This is in very, very high speed. That is about 1 lakh meter in 1 second. It travels 1 lakh meter in 1 second. With this speed, these are moving inside this metal in a zigzag direction. That in different direction, and they collide with the positive ions that we have already studied in the current and electricity chapter. You know very well. Now, even with this velocity they are moving inside this conductor, this particle may come up to this surface, but this electron cannot come out of this metal surface. Now why? So there is another force which is acting, which is pulling this electron inside the metal conductor. What is that force? That force is electrostatic force. When an electron tries to come out of this metal surface, this metal surface will become positive charge, and this will pull the electron inside the conductor. It will not allow the electron to come out of the metal surface. So all the electrons bound inside the metal conductor with an energy. We can say they are bound inside their nucleus or inside the metal surface with some energy which not allowing this electron to move out from this metal surface, even they are having a velocity of 10 to the power 5 meter per second. Now that is due to the electrostatic force, which is in the second most strongest force in the nature after the nuclear force. So if we able to provide an energy equal to this binding energy, the electron which are bind with some energy inside this metal surface, if we able to provide some external energy so that we can eject this electron from a metal surface, and we see that when an incident ray, that is radiation, is allowed to fall on this metal surface, electrons start coming out of this metal surface. That means we are giving some external energy to overcome that force. So in this way the electrons start coming out from this metal surface. They start eject out from this metal surface. So they need some minimum amount of energy, only then they can come out from this metal surface. What is that minimum amount of energy? So we can see here the work function of that metal. It is denoted by phi naught. So we can write the definition of this work function from here. The minimum amount of energy that is given to an electron so that it can just come out from the metal surface is called work function. Let me to write here the minimum amount of energy given to an electron so that it can just escape from the metal surface, surface is called work function. Work function. It is denoted by phi naught. This work function depends upon the nature of material. Different materials have different value of the work function. Now let me to write the work function of some material. Example for material. This work function is measured in electron volt. This is measured in electron volt. Electron volt is an unit of energy. So cesium, the work function of cesium is 2.14 electron volt. Similarly, we have sodium. The work function of sodium is 2.75 electron volt. Like aluminium, work function is 4.28 electron volt. Then we have copper. The work function of copper is 4.65 electron volt. Likewise, we have another element, that is platinum. The work function of platinum is around 5.65 electron volt. So we can see from this table that work functions of material are of different value. And you can see here the cesium has the least value of work function 2.14 electron volt, whereas the platinum has the highest value of the work function 5.65 electron volt. According to this work function of the material, we can eject the electron. So it is very easy to eject an electron from the surface of an cesium material than to eject an electron from the platinum, because the platinum material has a work function, the value of work function is 5.65 electron volt. If we are able to give an energy of 5.65 electron volt, only then electron can come out from the surface of platinum. But in case of cesium, it requires only 2.14 electron volt. Photoelectric effect has been explained on the basis of particle nature of light. Particle nature of light. According to Planck's quantum theory, he said that this radiation consists of a small packets of energy which is called as photon. Small packets of energy which are known as photon. So photon are the particle of radiations. So all radiations has a small particle which is carrying small packets of energy called photon. So let me to give you the full properties of photon first to explain the photoelectric effect. So now I will write one by one the properties of photon. All radiations consist of small packets of energy, small packets of energy called photon. Or we can say it as quanta. So these are actually the small packets of energy. They are carrying some amount of energy. The second point is these photons have definite amount of energy. This can be given as, written as h nu. Here h is the Planck's constant. This is known as Planck's constant. Nu is the frequency of the radiation. We can write it also as h c upon lambda. As you know that nu is equal to velocity of the wave divided by its wavelength. So since here we are taking the velocity of photon, so it must be the velocity of light. Instead of this velocity, we write here c. So you can write here nu is equal to c upon lambda. Now due to the shortage of time, we have to close today's lecture here. We will continue tomorrow. Thank you.